There are some news cycles that are just plain weird. And this news cycle tried really, really hard to be one of them. I saw headlines highlighting that JWST had observed methane and carbon dioxide in the atmosphere of a planet, which is entirely true. This was followed by stories that it could be aliens. And really, it is not enough data to be aliens. I want there to be definitive signs of life on other worlds. I want to know that life is common. I want the universe to be thriving with societies capable of art and exploration and empathy and science. I want our universe to not be a tremendous waste of space. And it's really frustrating to see these stories that inevitably imply that researchers like me are trying to cover up the truth. No, we're not. We're impatiently waiting for there to be enough evidence that we can say, yes, there is life out there among the stars. And that evidence isn't here. And those two weird mummy-looking things presented to the Congress in Mexico, those aren't confirmed aliens. Even Reuters did a debunking. They were undocumented origins, not studied by researchers, and presented by a journalist known for not always presenting science in ways researchers would call factual. It's not aliens. It is art. Art likely created by humans who needed some money, just like all those other headlines about NASA cover-ups and other things that imply researchers know how to keep secrets. Researchers live for our work to be shared. We want what we learn to land in school books and change the understanding of the world. When you see results, look to see who profits. If it's the textbook authors who have to rewrite their books, then you're seeing real science. This news cycle did not include aliens. Really, I wish it had. That would have been cool. What it did include are quasars, clusters, and the expansion of the universe, and a whole lot of big ideas that we're going to discuss right here on Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. One of the questions I get asked a lot and never know how to answer is, how close is the nearest black hole? The problem is, since black holes don't give off any light, we can only see them when they are eating objects that scream out with light and when their gravity radically moves around the things around them. It's entirely possible that a 3 solar mass black hole lurks somewhere between us and the nearest stars, completely unnoticed, within a few light years distance. It's not likely, but it's entirely possible. Their hidden nature leaves us guessing just where, oh where, are the black holes hiding? And a new paper published in the monthly notices of the Royal Astronomical Society and led by Stefano Tormenti has brought the nearest identified black hole from 1,600 light years away to just 150 light years away. The prior record was held by Gaia BH1, a 10 solar mass black hole discovered in 2022 through the motions of a sun-like star orbiting it at about the same distance our planet is from our sun. The new black holes, yes, that is plural, the new black holes were also found from how they are affecting the motions of stars, this time in the Hyades cluster. The data from this discovery also came from the Gaia mission. With its combination of precise imaging and spectra, it has the capacity to measure the complete three-dimensional motion of stars as they go both to and fro and back and forth in their orbits, both around our galaxy and around other stars. This amazing data, in combination with powerful computer models, allowed researchers to realize this system contains, well, more than meets the eye. According to Tornamenti, quote, "Our simulations can only simultaneously match the mass and size of the Hyades if some black holes are present at the center of the cluster today or were there until recently," end quote. It's possible that some or all of the black holes have already begun to exit the system, but the influence they had remains visible in the motions of the other stars. It's also possible they are still there, darkly moving among their luminous siblings. The presence of multiple extremely dark stars raises an interesting possibility. There could be sets of compact objects, such as a pair of black holes or a black hole neutron star pair. These kinds of pairs have the ability to radiate away gravitational waves and merge together over time. And these kinds of mergers give off a final bleep of gravitational waves that momentarily reshape our world in ways that can be detected by the LIGO, Virgo, and CAGRA gravitational wave detectors. Young star clusters can now be seen as sources of merging compact objects. And there's the amazing possibility that we'll someday detect gravitational waves from objects caught rearranging stars in nearby clusters. We don't know when this kind of a gravitational wave detection will be made. But as long as LIGO, Virgo, and CAGRA are powered up, the possibility exists. This suite of detectors are currently in their fourth observing run, called O4, with this season, which started May 24th, 2023. All detections are available through the Gravitational Wave Open Science Center. And there are even services that can push notifications to your phone and a website geared at the public where the latest alerts get posted. We'll make links to all these sites available on our website, EVSN.tv. While it's awesome to find black holes by looking at how they move and accelerate things moving near them, this isn't possible in every situation. What we can see at a distance is the energy released when black holes tear objects apart. Normally, this means seeing the light from a very dense disk of material around a black hole, either the material pulled off of a nearby star in a binary system, or material circling a supermassive black hole in the center of a galaxy. What is less common and truly awesome is when we see a black hole just pull something apart in an event called a tidal disruption. And normally this is a fast one-time kind of a thing where something is completely pulled apart. But one black hole has decided to be a dainty eater. First spotted by the Swift X-ray Observatory, this object, named Swift J0230, bursts with light about every 25 days. The X-rays are associated with a 2 million degrees Celsius event. In trying to understand exactly how a 2 million degree event can be triggered every 25-ish days, researchers first considered what similar objects exist and then did computer models. Currently, there are 2 other known repeating objects that are just partially disrupting whatever they're eating. In one case, a giant star gets nommed on every 114 days by a 78 solar mass black hole it is orbiting. In another galaxy, a white dwarf loses a chunk every 9 hours as it orbits a 400,000 solar mass black hole. This system, with a 25-ish day orbit, just might be an intermediate object. Their models estimate Swift J0230 is made of a 200,000 mass black hole that is taking 3 Earth mass bites out of a sun-sized star. According to lead researcher Phil Evans, quote, "This is the first time we've seen a star like our sun being repeatedly shredded and consumed by a low-mass black hole." So-called repeated partial tidal disruption events are themselves quite a new discovery and seem to fall into 2 types: those that outburst every few hours and those that outburst every year or so. This new system falls right into the gap between those. And when you run the numbers, you find the types of objects involved fall nicely into place too. End quote. The technology used to make this detection is new, and we can only hope that many more daintily eating black holes are found in the coming months and years. This research is published in Nature Astronomy. After a quick break, we'll be back with news on galaxies, and more galaxies. Stay tuned. Our universe has a lot going on, from gravity holding things together to magnetic fields funneling jets of material to electric fields making aurora and lightning pretty much wherever there is an atmosphere. There are a lot of forces doing a lot of things to push, pull, and twist everything into constantly evolving shapes and positions. Sadly, the only force that is easy to see doing its thing at a distance is gravity. It is easy to see how things get pulled together and how galaxies spin and orbit, but we're getting better at detecting the effects of other forces at a distance. And in a new paper in the journal Nature, researchers announce they have detected the effects of a magnetic field in the light of a galaxy shining from just 2.5 billion years after the universe formed. Cataloged as 9IO9, this galaxy's magnetic field was detected using the Atacama Large Millimeter Array, or ALMA. This kind of a telescope can detect how light rays are polarized. In a system with no magnetic field, dust grains should be more or less randomly oriented, and the light given off by the dust should have waves that are oriented in all sorts of different ways. In a system with a magnetic field, the magnetic field will align dust grains, and light will generally also have aligned polarizations. With ALMA, researchers could see that the bulk of the light had the same polarization and thus detect that a magnetic field should be present. According to lead author James Geach, quote, "Many people might not be aware that our entire galaxy and other galaxies are laced with magnetic fields spanning tens of thousands of light years. This discovery gives us new clues as to how galactic scale magnetic fields are formed." End quote. The research team believes that magnetic fields may arise during the first intense round of star formation experienced by a galaxy, and then persist and influence how each future generation of stars is formed. Now that ALMA has made this kind of a detection in one system, we can hope to see more galaxies similarly observed and more magnetic fields found, or not, and giving us data to understand what is really happening with these systems. There is a whole lot of astronomy that is, quite simply, looking at a bunch of similar things and hoping to find a trend. Some folks will refer to this as the leaf collection part of astronomy, where you go out, collect as many leaves, or in our case, galaxy or star images, and then group them up and declare, these are maple trees, or these are active galaxies. Depends on your science. This kind of work won't always get you the right answer, but it will give astrophysicists a starting point for building computer models and other tools to work out the science behind what we do observe and to periodically discover things are really not as we expected. It's really a scientific feedback loop. Astronomers see cool things. Astrophysicists explain the cool things and predict new things. And then more observations tell us where we are right, wrong, or sometimes so confused as to not even be wrong. One large area of study right now is the structure of the universe. We know fundamentally the universe is made of structures pulled together by gravity and voids left empty when everything got pulled out of them. This is the basic idea of the large-scale structure of our universe. We also know from theory that in the earliest few 100,000 years of our universe, things were just too hot to allow material to collapse into structures. And the push and pull between gravity trying to collapse material and the gas laws we learned in school trying to expand the heated gas into a larger volume, well, that imbalance led to the formation of what are called baryon acoustic oscillations that traveled like sound waves through the early universe. In the cosmic microwave background radiation, we see these waves reflected in the sizes of the hot and cold spots and their frequency. We know from theory that those hot and cold spots should have grown into the mass-rich clusters we see, as well as vast voids. But we hadn't seen any of these voids, at least not until now. In a new research paper appearing in the Astrophysical Journal and led by Brent Tully, researchers describe a massive bubble 820 million light years from Earth that appears to be the first baryon acoustic oscillation associated void thus far discovered. While your normal gravity pulled everything out of this region kind of a bubble has been seen many times, the voids created by baryon acoustic oscillations are distinctly different. They are predicted to have a massive cluster in their centers, like some splashback from the process that created the void. They also should have a bubble of material surrounding them, a sphere-like bubble, while voids formed by gravity are shaped at the whim of the surrounding mass distribution. They are naturally occurring structures that are weird. This new void has the Bootes supercluster in its heart, and its walls include the Coma and Hercules clusters, as well as the Sloan Great Wall. This should be one of those wonderful, and the science is exactly as expected kinds of celebration moments, but there's one flaw in what we see. This structure is actually larger than our theories predicted, and that reinforces the fact that there is just something missing in our understanding of how the universe formed and evolved. We don't know what is missing. We just know this is yet one more line of evidence that says things seem to have formed larger and faster than expected. We're still very much at the leaf collecting stage of this research. The larger things are going to be the easiest to find, and it could just be we're only seeing the statistical weirdos. Although really, we are probably missing something. I can only hope more data will quickly lead us to new understandings. Getting that new understanding, as I feel like I say every week, isn't easy, but does get some assistance from gravitational lensing. The mass of large galaxies and the larger mass of galaxy clusters can actually bend light and increase the amount of light we get here at Earth in ways that are similar to how magnifying glasses can increase the light hitting a single spot on the ground. The JWST is an ideal instrument for detecting the gravitationally lensed light from distant galaxies shining at us from the early universe. The expansion of our universe causes light to stretch as it travels toward us, with blue light from the early universe appearing to us as red here in the current universe. JWST can see these red shades of light with higher resolution and greater sensitivity than any other telescope. A year into its science operations, we're seeing paper after paper highlighting the farthest, faintest, and weirdest galaxies ever seen. And this week was no exception. In a trio of new papers in the Astrophysical Journal and Astronomy and Astrophysics, researchers describe JWST observations of the El Gordo galaxy cluster. This massive system is located about 7 billion light years away. And with hundreds of measurable galaxies, it is the largest galaxy cluster seen at this distance. Its mass and size allow El Gordo's gravity to wonderfully lens the early universe into view. According to Brenda Fry, who led one of the three papers, quote, "Lensing by El Gordo boosts the brightness and magnifies the size of distant galaxies. This lensing effect provides a unique window into the distant universe." End quote. My favorite discovery in these papers came from Fry's work. Her team, which includes 9 students of all ages, found 5 lensed galaxies that appear to be at the same distance, as well as an additional dozen galaxies that appear to potentially be at the same distance. The light from these 17 galaxies has been traveling for 12.1 billion years. And it's possible these galaxies are part of the most distant galaxy cluster ever discovered. Put another way, they used the most distant large galaxy cluster we know of today to magnify light and discover what could be the most distant forming galaxy cluster of tomorrow. It really is galaxy clusters all the way down. These 3 papers also discover a tiny irregular galaxy that was discovered, and then a process was used to transform the distorted light into a clearish image of the system, as well as a distant galaxy with one star shining above all the rest. The light from that red giant star has been traveling for around 11 billion years, and it is the most distant red giant ever seen. All these largest, most distant, brightest, faintest, and other extraordinary systems are defining what is possible. Now we just need to figure out how it is possible. After a break, we're going to dive further into the physics that explains how our universe came to exist in its current shape and diversity, and how we know our understanding of that physics still needs a bit of work. Stay tuned. Those of you who watch the show on Now Media or YouTube may notice that some weeks I have glasses and some weeks I don't. This isn't because I wear contacts, but rather it's because I'm just starting to need glasses, and I can get away without them as long as I don't want to read any of the small notifications that may pop up on one of our studio's screens. For those pop-ups, there's a lot of tilting my head, sometimes closing one eye, and then squinting to try and figure out what those notifications say. I can usually make things out, but there can be errors in what I read because my eyes just don't have the resolution those pop-ups demand unless I wear glasses. This kind of a can just make it out, pushing things right up to their optical limits, isn't unique to stubborn Gen Xers who refuse to admit they now need glasses. Astronomers, we will push our telescopes up to and often past the limits of what they are designed to do because our curiosity outpaces the development of new technology. Nowhere is this pushing of limits more apparent than in the field of cosmology, where researchers work to understand how the universe formed, how it continues to evolve, and even how it will one day end. Using the Hubble Space Telescope, researchers have worked to measure the expansion rate of the universe by looking at a variety of what we call standard candles. These are sources of light that have a well understood luminosity like a 100 lumen light bulb has. And because we know how much light they give off, we can measure how bright they appear and calculate their distance. This is something your brain does automatically. When you judge a faint motorcycle light to be further away than a brighter one, that's your brain measuring distance. With telescopes and computers, that thing your brain does can be done to hundreds and thousands of objects across the sky. One particular kind of star, the Cepheid variable star, is particularly useful for this kind of work. These stars are extremely large and bright, and they change in brightness over time in ways that are directly related to their luminosity. This means that when we see a star change in brightness every 10 days, we know exactly how much light it gives off. And when we see a star vary every 32 days, we also know exactly how much light that star gives off. This is all pretty straightforward. And Hubble Space Telescope did a really good job measuring stars in all our nearby galaxies. But if we want to understand the expansion of our universe, we want to push our data set out to galaxies as far away as possible. And Hubble can only do so much. The Hubble Space Telescope was designed to fit in the space shuttle's school bus-sized cargo bay. Its primary mirror is just 2.4 meters, or just shy of 8 feet across. For a modern telescope, that just isn't very large. And the resolution of a telescope is related to only two things: the size of the mirror and the color of the light being observed. As the mirror gets larger and the wavelength of the light gets smaller or bluer, we can see more and more details. With Hubble, the mirror size is constant. And the color of the light we see from the Cepheids is pretty red, which is a longer wavelength. So Hubble is good, but separating the light of individual stars can sometimes get a lot like me trying to read those tiny notifications. I can do it, but there are errors. For the stars, sometimes things are measured as being brighter than they are because light from another object gets added in. Sometimes things will get seen as a bit fainter than they are because attempts to remove the interloping light removes a bit too much light. The average should be true, but that scatter up and down leaves room for doubt. And right now, our understanding of the universe is confusing enough that we want to remove all room from doubt from all our measurements. About 10 years ago, researchers realized that our understanding of how fast our universe is expanding based on looking around at our nearby universe, and our understanding of how fast the universe should be expanding based on observing the early universe, just don't match. This is uncomfortable. Both sets of data have multiple lines of evidence that point to some number, and those numbers are similar, but not within error of one another. We can't find any way to adjust our measurements to allow things to fit. It's like trying to put a twin fitted sheet on a double bed. At first it looks like it should work, but it just doesn't. Only instead of being left with a disappointing sheet, we are left with an overly fast expanding universe, which is not something anyone ever expected. And when two sets of research come up with two mutually exclusive numbers to describe our expanding universe, we know there's something wrong. We're pretty sure this is an us thing. We're pretty sure there's just something missing in our understanding of either gravity or the particles that make up our universe or some combo of these things. And That gap in our understanding is the reason we get different values from looking at the modern universe and looking at the early universe. But at the end of the day, it would be a whole lot easier if it turned out we just screwed up in our observing. And until we can prove that we didn't screw up, people are going to keep asking, are you sure you didn't screw up? A newly accepted paper in the Astrophysical Journal, led by Adam Rees, uses the JWST to make it very clear. No, we did not screw up when we made the Hubble measurements of Cepheid variables. In this paper, the researchers describe how the larger mirror of the JWST is able to better resolve the individual Cepheid variables in a variety of galaxies. They replicate earlier work done by the Hubble Space Telescope and get the same average results with a lot less noise or error in the measurements. As Rees explains, quote, "This kind of improvement is the stuff astronomers dream of. We observed more than 320 Cepheids. We confirmed that the earlier Hubble Space Telescope measurements were accurate, albeit noisier. What the results still do not explain is why the universe appears to be expanding so fast. We can predict the expansion rate of the universe by observing its baby picture, the cosmic microwave background, and then employing our best model of how it grows up over time to tell us how fast the universe should be expanding today. The fact that the present measure of the expansion rate significantly exceeds the prediction is a now decade-long problem called the Hubble tension. The most exciting possibility is that the tension is a clue about something we are missing in our understanding of the cosmos." End quote. This is your friendly reminder that scientists do science because we don't know everything, but we want to. And gaps in our understanding are exciting puzzles we can pull apart like knots over a year, over a lifetime, or sometimes across several generations. It has somehow been an entire generation since the 1998 discovery that our universe appears to be accelerating apart over time. Rees was a graduate student on one of the two papers that highlighted this discovery, and he received a Nobel Prize for that work. For the past 25 years, he and others have continued to ask, how? Just how does the universe accelerate apart? And we have no idea, but that's okay. That doesn't mean what we know is wrong. It just means our understanding is incomplete. For nearly 300 years, we understood how orbits worked and could calculate them using Kepler's equations and Newton's physics, except for Mercury. Something about that little planet snuggled up to the sun was causing it to orbit not quite as predicted. It was a tiny effect that was almost, but not quite blamable on mistakes in observing. That difference between Newton's theory and what was observed was explained by Einstein's theory of relativity, which makes it possible to see how large masses can distort space-time and affect the behavior of objects moving super fast or moving super near large masses. With the addition of relativity to our understanding of gravity, we expanded our understanding. Everything we knew from Newton remained true, but there was a bit more knowledge needed in extreme circumstances. And let's face it, trying to understand the entirety of our universe is an entirely new extreme. It could be that at this scale, there are new forces or new effects in addition to gravity. Or it could be that over large enough distances and times, gravity has an additional term that would get added on to Newton's and Einstein's equations to further modify things. We don't know. But we now know HST and JWST are consistent in their measurements of our modern universe. And folks like me hope that JWST will allow us to push our understanding out to greater and greater distances, bridging the early universe to the modern universe. Time will tell. But right now, we have a massive unknown, and that is both awesome and frustrating. But JWST has only been doing science for a year, so we remain hopeful. New results are coming, and when we have them, we'll bring them to you right here on EVSN. After the break, we're going to turn from the distant universe to modern technology and take a look at OSIRIS-REx's upcoming sample return. And also, we'll look at this week's rather abbreviated Tales from the Launchpad. Stay tuned. One of the weird sadnesses among our production team is I am probably the least interested in rockets among all our writers, and I'm the person who has seen the most launches in person. This is partly a fluke of age. I'm old, and it's also geography. Eric graduated college during the pandemic and can't just drive to Florida from his Twin Cities location. I'm in St. Louis, and in the days before the pandemic, I got to see a variety of launches, both as a journalist and a fan. And I got to fail to see a bunch of launches I tried to see as a journalist and a fan. If you followed me on Twitter in December 2019, you got to experience my 7 days of not seeing any of the 4 planned launches. But I digress. The last launch I saw was in 2016 when the OSIRIS-REx mission took off from Cape Canaveral. That mission was kind of an exception to my normal journalist or fan reason to see a launch. While I did watch the launch from the media area, I had 5 students watching along with other mission team members because our team at CosmoQuest was working with the OSIRIS-REx team to develop software that would allow the rapid mapping of features of boulders and rocks and craters that cover the asteroid Bennu's surface. Our shared goal was to prepare to map, and then map the asteroid after OSIRIS-REx reached it in late 2018. OSIRIS-REx had a spectacular takeoff, and everything went according to plan, up until we got back our first images of the asteroid. We'd expected an object with large, smooth areas that would be safe for the spacecraft to grab a sample from. Bennu decided to defy expectations and be one giant rubble pile. During the summer of 2019, the CosmoQuest community mapped Bennu. More specifically, Bennu mappers launched on May 22, 2019, and ended a mere 92 days later on August 21st. During this time, 3,640 community members examined 4,509 images which had been collected by OSIRIS-REx during its 2 years of orbiting Bennu. They were tasked with identifying and marking rocks that exceeded a minimum size. Each image was marked by 15 people, which amounts to over 14 million total marks. This data was then forwarded to the OSIRIS-REx team and used to help them identify safe candidate landing sites, including Nightingale Crater, where the sample was collected. We weren't prepared for that rocky challenge, but we decided failure wouldn't be an option, and we mapped. And we mapped, and we mapped. And on October 20th, 2020, in the dark of the pandemic, the mission navigated OSIRIS-REx down to Nightingale Crater, discovered the asteroid has the consistency of a ball pit as the spacecraft accidentally stabbed its arm 30 centimeters into the asteroid, and then safely, somehow, pulled away with far more rock sample than we ever anticipated. This led to a few issues getting everything closed up, but it's estimated that the mission, which did manage to safely seal up its sample, is coming back with 250 grams of asteroid Bennu. OSIRIS-REx departed Bennu on May 10th, 2021. And on September 24th, potentially the day you are watching this, that sample is expected to be returned to Earth. We will be doing live coverage as we can on twitch.tv/CosmoQuestX. And in our next episode, we're going to be doing a deeper dive into this mission and just what it means when we say something is a rubble pile of an asteroid. For now, we are just keeping everything crossed that the sample will make it safely from space to a lab here on Earth. The math that goes into this is amazing. They are essentially firing the sample at our planet as the spacecraft flies past. And they are doing it with enough accuracy that they know it will come down in the Utah desert. I wish the team the best of luck. It has been a wild 7 years, and being part of mapping that asteroid is definitely one of the high points of my life. Okay, enough Bennu. Next up, I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launchpad. Hey, Eric.
Hi, Pamela. It was a pretty light week since our last show, but we still have interesting things to talk about, so let's get started. First up, on September 8th, was the suborbital launch of Galactic 3 carrying passengers aboard Virgin Galactic Spaceship 2. As usual, the flight carried 6 people, 2 pilots, chief of astronaut training, and 3 paying passengers. Virgin Galactic hopes to increase this to 4 paying passengers soon. The 15-minute flight was successful. Let's watch part of its flight. The other launch this week was a relatively rare Atlas V launch carrying the Silent Barker payload, or payloads as some sources describe it, as a group of satellites, into orbit for the National Reconnaissance Office. The only thing publicly released about the mission is that it's a joint venture between the NRO and the Space Force. We also know it will operate from geostationary orbit, where it was sent directly by the Atlas V 551 rocket. ULA streamed the launch, but ended coverage just after fairing separation at the request of the NRO. We still have the liftoff to show you, though. In addition to the Virgin Galactic suborbital launch and the NRO launch were 2 Starlink launches, one from each coast, and a classified Chinese launch. And we'd just like to say, as you're going into recording, Soyuz MS-24 launched with 3 Russians and an American on their way to the ISS. More on that next week. We keep track of orbital launches by launch site, also called spaceport, according to RocketLaunch.live. So far this year, USA has had 71 launches, China 42, India 7, Kazakhstan and Russia each have had 6, New Zealand 5, Japan 3, French Guiana and North Korea each have had 2, and Israel, South Korea, and the United Kingdom each have had 1. Of these 147 launches, there have been 6 failures, reminding us that space is hard.
Thanks, Eric. Before we go, I'd like to highlight the 2023 Chemistry and Geology Prize from the Ig Nobel Awards. The Ig Nobel Prizes honor achievements that make people laugh, then think. The prizes are intended to celebrate the unusual, honor the imaginative, and spur people's interest in science, medicine, and technology. This year's Chemistry and Geology Prize was awarded to Jan Zalazeswitz for explaining why many scientists like to lick rocks, and it references their paper, Eating Fossils. In this paper, Jan writes, quote, The rock lying by the roadside did not look like much of interest at first. A rather nondescript limestone with little more to show to casual observation than a few vague blotches. Anyway, old habits die hard, so I picked it up, licked the surface, and put it and my hand lens to my eye. Licking the rock, of course, is part of the geologists' and paleontologists' armory of tried and much tested techniques used to help survive in the field. Wetting the surface allows fossil and mineral textures to stand out sharply, rather than being lost in the blur of intersecting microreflections and microrefractions that come out of a dry surface. End quote. This paper goes on to explain how variations in taste have aided in classification and allowed some to literally develop a taste for rock. Every geologist on our team nodded sagely with this news and agreed. Rocks are meant to be licked. I, for one, am glad to have chosen a definitively don't lick your science profession. Don't lick the stars, just don't. And I would like to remind folks, you don't know where those rocks have been, and lab equipment exists for a reason. But to each their own. Next week, we'll be looking in depth at the Physics Ig Nobel Prize. The science is a bit fishy, but we think you'll enjoy what anchovies have to do with climate change. And that's it for now. Good night, everyone. And remember, go outside and look up.